Hi everyone, this is section 5.1, exponential functions and growth and decay. Originally in the calendar I had this set aside as two separate videos and homework assignments, but I decided to make it all one video and you'll see only one homework assignment in my math lab. So just be aware of that. You only have one homework and one ed puzzle to go along with this section. The objectives for this section are to graph and apply exponential functions. We're going to talk about asymptotes and finding horizontal asymptotes. We're going to graph and apply exponential growth and decay functions, and then we're going to compare transformations of graphs for exponential functions. All right, let's get started. So we're going to start out with just the general definition of an exponential function first. It says if b is a positive real number and b does not equal 1, then the function f of x, or y, equals b to the x is an exponential function. The constant b is called the base of the function, and the variable x is called the exponent. So we would read this f of x equals b to the x power, or the exponential function of base b to the x power. Recall that a linear function has a constant rate of change. That's where all of our outputs change. They're increasing or adding or subtracting by the same number over and over again. An exponential function, we're going to notice, is a little bit different. Instead of adding or subtracting the same number over and over again, we are multiplying the same number over and over again. So that's going to be something you're noticing as a pattern in these. And that b value, the base, is actually what's getting multiplied from one term to the next. It's also important to remember that an exponential function has a variable in the exponent. So that's going to be one of the easiest ways to tell that you have an exponential function because your variable is in the exponent. Another thing I would make a note of in your graph, your notes, is that b must be a positive number and it can't equal 1. If b is a negative number, if you have a negative base, it's not an exponential function. And again, if it's equal to 1, it is not an exponential function. All right, so if we look at the bottom here, we've just got a list of functions and we want to determine which are exponential. We're looking for some of those properties. We want a positive base. We want it to be in the form base b to the x power, where b again is a number that's positive. We want to make sure we have our variable in the exponent also. So if we look back at these functions at the bottom here, the ones that meet that criteria are c, y equals 3 to the x, where 3 is our base. D, y equals 2/3 to the x, where 2/3 is the base. We say a is not exponential. That's actually a linear function. Notice that y equals mx plus b form. B is not a exponential function. If you have a variable to a power where you know the power, where the power is not a variable, that's one of our polynomial functions. And then also e, y equals e to the x, will be an exponential function. E is actually a number. It's an irrational number, kind of like pi. So we will talk about that a little bit more in this lesson today. E is exponential and f is not exponential, again, because that variable is not in the exponent. So there's 3 examples there for you of what a basic exponential function looks like. Okay, evaluating exponential functions, we're just plugging numbers in here. You can use your calculator to help you if you want. These are meant to be ones that you can use your exponent rules, review from previous sections to simplify. So for example, if I have f of 4 here, I would plug 4 in for x, so 2 to the 4 minus 5 power. If we're evaluating an exponential function, you want to treat that exponent kind of like a parentheses. An order of operations says we want to simplify that first. So 2 to the 4 minus 5 will simplify to -1. 2 to the -1, remember negative exponents, we can make them positive by moving a number into the denominator. So I can make it 1 over 2 to the first, that's our negative exponent property, and then 2 to the first gives me 2. If you type in 2 to the 4 minus 5 power in your calculator, it's going to tell you probably the decimal equivalent of this, or 0.5. All right, let's look at another one. Here I'm evaluating f of -2. So that would look like -3 times 10 to the -2nd. 10 to the -2nd, again, I want to write that with a positive exponent. So I'm going to make it 1 over 10 squared, or 100. I can just simplify that. And then if I multiply these together, I'll have negative 3 over 100. Again, if you typed this in your calculator, the calculator would give you the decimal equivalent of this, which would be negative 0.03. In the next problem, I have 1/7 to the x power, and I'm evaluating it for 1/3. So I'm really doing 1/7 to the 1/3 power. Now remember what we talked about with rational exponents before? If I see 1/3, that's the same as the cube root of 1/7. This does not reduce, so this is one you'd want to put in your calculator, either 1/7 to the 1/3 or the cube root of 1/7, and I'll just kind of do that off to the side in my calculator. I'm just going to do 1/7 to the 1/3 power, and I get approximately 0.523. So it depends if you were doing something like this in my math lab, what it would be asking for. An exact answer would be that cube root of 1/7, and the approximate answer would be 0.523. Okay, last one of these. Here I want to do 4 to the negative 3/2 power. So the first thing I'm going to do is I'm going to make that exponent positive. So I'm going to move the 4 to the 3/2 into the denominator. And then I can think of that 3/2 as 3 times a half. So I can split it up one of two ways. I can either make the 4 to the 3rd power and then take that to the 1/2. And this would be equivalent to this guy because this is the power to a power rule. 3 times a half would take me right back to 3/2. Or I could make it 1 over, I could do the 1/2 power first and then to the 3rd. Now either one of these you can evaluate in your head. 4 to the 3rd, or 4 times 4 times 4 gives me 64 to the 1/2. And then if I simplify 64 to the 1/2, that just means square root of 64, and that gives me 1/8. Now if I look at the one on the right, if I do the parentheses first, 4 to the 1/2, that means the square root of 4, which gives me 2. And then take that to the 3rd power, 2 to the 3rd, or 2 times 2 times 2 also gives me 1/8. So a couple different ways that you can think about that one. Again, if you did this one in the calculator, it would give you a decimal equivalent of that, which is 0.125. Okay, so now let's talk about exponential growth and decay functions. These functions are going to have a value in front of that b to the x. They use a in this textbook. So we're going to use the model y equals a times b to the x. A in this function represents some sort of initial value or starting amount. And also notice that a is going to be our y-intercept on the graph. And I'm going to put arrows on either side of this. There should be arrows there. B for exponential growth will be a number larger than 1. Now remember, b can be a positive number, so it could be a fraction as well, like a half or a third, something like that. And that's going to be our other type of exponential model that we'll talk about in a moment. B represents the growth rate. So remember we said an exponential function is when you're multiplying constantly from one term to the next, and that b value is what we're multiplying by. So if we're multiplying by a number bigger than 1, you can imagine that that's going to make something grow, and it's going to make it grow pretty rapidly, and we'll see some different values plugged in for these numbers. Okay, so the graph is going to look something like this picture. Let's talk about the properties of this, starting with domain. Domain is all of our x values, or how far this graph goes from left to right. The domain of exponential growth functions is all real numbers. Negative infinity to positive infinity. It goes forever to the left and forever to the right. The next thing I'm going to talk about is an asymptote. An asymptote is a line that your graph gets close to, but it doesn't touch. And these exponential growth functions are going to have an asymptote on the x-axis. Or we could say that's the equation of the line y equals 0, a horizontal line at 0, which is right here. Okay, so you can see it kind of looks like my graph is getting close to that. And in fact, if you graph an exponential growth function in your calculator, it's almost going to look in the calculator like it does touch the x-axis. But actually what's happening is it's getting infinitely close to the x-axis. That's because it doesn't matter what number I plug in for x, I'm always going to get a positive number out, because a positive exponent is going to make it larger, and a negative exponent, remember negative exponents don't give us negative numbers, they actually give us reciprocal values, which give us really small fractions. So no matter what we plug in, we're always going to get a positive number, and that means we're going to get really close but not touch the x-axis. That means our range is only positive numbers. So we're going to say 0 with a parentheses to infinity. Again, it's going to be a parentheses there because we can't equal 0. We can't touch 0. That's when we would use a bracket if it was equal to 0. Intercepts, we have a y-intercept at A, where you could say the point 0a. It's labeled on this graph here. Increasing or decreasing, this function is increasing from left to right. My values are always going up. And is it concave up or concave down? This is a concave up graph. So we saw some of those terms before in some previous sections. Okay, so that's what exponential growth looks like. And if you are talking about the shape of this graph, we call it an exponential curve. Something that grows, maybe, there it goes. Something that grows very slowly at the beginning and then begins to grow very quickly later on. Okay, so that's going to be a shape we're looking for later. The other type of model that we're going to talk about very similar is exponential decay. So you can see here that we still have that same sort of shape. Again, we call it an exponential curve. The difference here is if we're following this graph, it decreases very rapidly, and then it starts to decrease slower, again, as we get closer to the x-axis. Notice it's the same model here, y equals a times b to the x, where a is some initial value or your y-intercept. B, this is the big difference between growth and decay. B is a value between 0 and 1. Remember, B can't be a negative number, can't be equal to 1. So we're really concerned about, is it smaller than 1 or bigger than 1? Multiplying by something smaller than 1, like a half, you can imagine is going to make values smaller. And that's why we're seeing a decay along our values. Again, multiplying by something bigger than 1 is going to make that grow. A and B, I'll just highlight those for you here. Again, represent the same values. Let's talk about domain. Domain is still all real numbers. Goes forever left and right. It's nice because you have no restrictions on these. Asymptote is still the x-axis, or you could say the line y equals 0. Range is all values from 0 to infinity. Can't be equal to 0, can't be negative. Intercepts, we have a y-intercept where it crosses my y-axis at A. You do not have any x-intercepts because it doesn't cross that x-axis. This function is decreasing from left to right, but it is still concave up, we would say. Okay, so let's practice some graphs of these. You're going to need a graphing calculator to fill out a table of values. I'm going to start with the values -2 to 2 in a table. You can pick really anything you want here because the domain is all real numbers. But these are good values to start with. What we're looking for is values that curve up or curve down, and hopefully we see if it's approaching a certain value. And we'll kind of talk about what that looks like. If you feel like these points don't give you a good enough picture, you could always make a larger table of values. All right, so plugging these in, and I'm going to use my calculator for these. I'll just show you what the first one would look like. It would be 0.05 times 2 to the -2 power. You've got a negative in the exponent and a -2 I'm plugging in, plus 2. And I'm just going to type that in exactly as you see it written there in my calculator. So 0.5 parentheses 2, and then my exponent, negative parentheses, -2. Make sure you're using the negative key in your calculator, not a minus, and then plus 2. And that all simplifies to 4. Now in your graphing calculator, if you hit second and then enter, it will bring up the last thing you typed in, and you can just change that -2 to a -1. Saves you some time, or you can type the whole thing in again. If I plug in -1, I get 3. Plug in the same thing again. This time it's going to be a 0 in for my x. I'm going to get 2.5. If I plug in 1, I'm going to get 2.25. And then if I plug in 2, I'm going to get 2.125. And you'll notice what's happening in these y values here. I'm getting closer and closer to the value of 2. My values are kind of leveling out. So that's going to help me when I graph it. Let's plot these points. -2, 4. -1, 3. 0, 2.5, 1, 2.25, 2, 2.125. And there is my graph. Because I saw that we're getting close to 2 on my y values, I'm going to draw in that horizontal asymptote. Again, it's a line that my graph is going to get close to, but not touch. And then I know not to cross that when I make my curve. Now, if you didn't see those y values getting close to a number kind of leveling out, then you would just extend your table of values until that started to happen. But we're going to talk about something that's kind of helpful in a little bit that'll give you a clue in the equation. Domain for these functions is always all real numbers. And you can see that in this picture as well. It goes forever left and right. My asymptote in this graph is a horizontal line at 2. And remember, horizontal lines always start with y equals. So y equals 2 is my horizontal asymptote. My range then is all the values above 2. So 2 to infinity. Okay, let's try another one of those. Here we have 9 times 2/3 to the x plus 1 power minus 3. And again, I'm going to start with negative 2 to 2. And then from there, I can always make it more in my xy table if I need to. So let's say I was going to plug negative 2 into this function. It would look like the following. 9 times 2/3 to the negative 2 plus 1 power minus 3. So again, you can use your calculator. Just type that in. 9 parentheses 2/3. Your exponent key, negative 2 plus 1, and then minus 3. And I get 10.5. Okay, and now we'll just continue with that. I'm going to plug negative 1 in for x. That gives me 6. If I plug 0 in for x, I get 3. If I plug 1 in for x, I get 1. If I plug 2 in for x, I'm getting negative 1/3. If I plug 3 in for x, I'm going to keep going because I can't really tell where that's approaching yet. I get negative 1.2 repeating. If I plug in 4 for x, negative 1.8 approximately. I'm going to keep going. I need some more values here. I want to see where I'm leveling out at. 5 in for x. And these values are getting closer and closer together, so I know I'm going in the right direction here. I wouldn't want to plug in like negative 3 or negative 4 because those were getting bigger and further apart. If I plug in 5, I get about negative 2.2. They're getting closer. If I plug in 6, I got negative 2.5. Let's do one more. If I plug in 7, I get negative 2.6. And you can see we're getting pretty close there. So I'm going to say that my horizontal asymptote is at negative 3 is what we're getting close to now. Okay, let's plot some of these points. Negative 2, I was at 10.5. Negative 1, I'm at 6, 0, 3, 1, 1, 2, negative 1/3. Let's go over to like 5. I was at negative 2.2. We'll plot all of them, but we know that that's that shape we're looking for, that exponential curve. This one looks like it's decaying. It's decreasing from left to right. And again, we want to make sure that we don't cross that asymptote. So now my properties. Domain is always all real numbers. That's an easy question. My asymptote here is y equals negative 3. That's that line, always a horizontal line, always going to be a y equals in front of it that my graph is approaching but not touching. And then my range is all the numbers larger than negative 3. So negative 3 to infinity because my graph is above that axis. Okay, so now let's look at this problem and the previous one. For this one, if you look at your equation, notice we had an asymptote at y equals negative 3. Let's go back to the previous one. Let's look at our equation. we had an asymptote at y equals 2. Hopefully you're seeing a pattern here. This number that we're adding or subtracting on at the end, 2 and -3, remember what those numbers do if we do that to a function. If we're talking about transformations, and we'll review this in a minute, that's shifting my graph up or down. And when I shift an exponential function up or down, it shifts my asymptote up or down. So if I shift the graph up 2, my asymptote moves from 0 to 2. The 0 is where it starts for in our basic functions. Or if I put a -3 at the end, it shifts my graph down 3. So it takes my asymptote from, again, 0, the x-axis, down 3 units to -3. So that could be helpful if you're searching for that asymptote and you're not quite sure where it's leveling out at. Look for that number that's added or subtracted on at the end. That's going to be the number that you're looking for your values to get close to have a good picture of these graphs. Okay, here is a problem for you guys to practice. So start with -2 to 2. Fill out those values in the table, and then you can either extend the table into smaller x values or larger x values if you feel like it's necessary. Sketch your graph, name, domain, range, and asymptote. Okay, let's see how you did with this. So when I plugged in -2, I got something really close to 4, 3.99. When I plugged in -1, 3.98 or 99, depending how you round that. If I plug in 0, 3.963. If I plugged in 1, I got 35/9 was the fraction. Let's see what they get, 3.8 repeating. If I plugged in 2, I got 11/3, which was 3.3 repeating. Oh, no, 3.6 repeating. Here we go. I'm going to give you a few more values here. Plug in 3, you get 3. Plug in 4, you get 1. Plug in 5, you get -5. So that's going to show you that growth or decay there. All right, so let's plot these points. -2, really close to 4. -1, really close to 4. 0, really close to 4. 1, really close to 2, 3.6. We're getting down a little bit there. 3, we're at 3. 4, we're at 1. 5, I'm way down at -5, and then hopefully you're seeing that kind of curve shape here. This graph has been reflected upside down. That negative out front reflected it over the x-axis. That's a transformation we've talked about before. And again, notice I added 4 at the end here. So you should have had y equals 4 for your asymptote, domain, all real numbers, and then range here, hopefully you were careful. It's not everything above 4, it's everything below 4. So we would say all values less than 4 or -infinity to 4 instead of 4 to infinity if it was above the axes. Okay. If you ever want to check these graphs or check anything you're not sure about, you can always, with your graphing calculator, put this equation in y equals and just hit zoom 6, get a really standard view of the window there and see if that helps you. You can also use the table of values instead of hitting graph. If you hit second graph, you can see a table, and that can help you fill some of these out kind of quickly as well. Okay, so transformations, we've seen some rules like this before, so I just want to review them very quickly here. We've already kind of mentioned in this lesson that if you have a vertical shift, up or down, that's where we're going to add a number onto the end. So that would look something like this. If we talk about our general b to the x being our exponential function, a number added on at the end, let's call it k, we'll move it up or down. Okay, depending on if k is a positive, it's going to move up, and if k is negative, it's going to move down. A horizontal shift is a left-right shift, and where you're going to see that occur at in the graphs is you're going to see it in the exponent. Now we're talking about inside our function being in the exponent when we have an exponential function. If h is a positive number, well, I shouldn't, I don't like the way they word that here. Let's take that out. I'm going to change this a little bit. So let's call this b to the x plus h. Here we go. If h is negative, it's going to move it to the right. And if h is positive, it's going to move it to the left. So for example, that'll follow along with our rules that we talked about before. That'll be a little bit easier. For example, if I had b to the x plus 3 power, that would move it to the left 3 units. Or if I had b to the x minus 5 power, that would move it to the right 5 units. And we'll practice those on a little bit so you can see what that looks like. Okay, next we have our reflections. If we reflect across the x-axis, you're going to see a negative in front of the function. And if it's a reflection over the y-axis, you're going to see a negative next to the x again in the exponent. Vertical stretches or compresses will be that a value out front. If a is a number larger than 1, it's going to stretch. And if it's a number smaller than 1 but bigger than 0, remember a is always going to be a positive number for us, then you will have a compression or a shrink. And then finally, horizontal stretch or compression, that's if you have a number multiplied on the inside. It's going to stretch if you have a number smaller than 1, and it's going to shrink or compress if you have a number bigger than 1. So these are actually all of the same rules that we saw before with transformations. The only difference now is we're applying it to a new type of function. You just want to remember that anything inside the function is going to affect it by either a reflection over the y-axis or some type of horizontal movement, either a horizontal stretch or shrink or a horizontal shift. And those you'll see inside the function, it'll actually be in the exponent. So that's what we're looking for. If something is not in the exponent, if it's out front of our b to the x, or if it's a number added or subtracted on at the end, those are going to be our vertical movements, a vertical stretch or compression or a vertical shift up or down. So let's practice these rules a little bit. You can kind of see what these look like. So let's say I have just the basic exponential function y equals 4 to the x. So this would be an example of an exponential growth function because my base is larger than 1. And I want to compare, let's start with this graph, y equals 4 to the x minus 1. Now you'll notice the difference in the two functions is that there's an extra little minus 1. Because that's happening inside the exponent, inside the function, and it's a number added or subtracted on, it is a horizontal shift. Because it is subtracted, that means it is a shift right 1 unit. Okay, let's look at b. I have y equals negative 4 to the x power. Anytime you have a negative either in front of your function or in your exponent, that's going to be a reflection. Here we have a reflection because it's out front over the x-axis. And that's the difference between the two graphs. Finally, let's look at one that has a lot of different transformations here. There are 3 different things that are happening. We have a 3 multiplied out front, a minus 2 on the inside of the function in our exponent, and a minus 3 at the end. The 3 out front is a vertical stretch or shrink. Because it's a number larger than 1, it's going to be a vertical stretch. So it's going to make it 3 times as tall, and you could say by a factor of 3. Sometimes they'll say that. Minus 2 inside my exponent, again, will be a horizontal shift because it's a minus. It'll move it right 2. And then finally, if I have a minus 3 at the end, that's an up or a down because it's negative. It moves the graph down 3 units. So that's the difference between this function and the original function that they started with that they used as a base function, y equals 4 to the x power. Okay, so here's a problem or a set of problems for you to practice. The goal here is to try to match these using your knowledge of transformations. So what I would suggest doing is name the transformations that are occurring in each of these functions. So I'll get you started out. Number 1, y equals 4 to the negative x. If y equals 4 to the x is our basic function and there's a negative on the inside, it's a reflection over the y-axis. So then you want to use that knowledge to figure out which of the following graphs looks like an exponential growth function, which is this shape here, that's been reflected over the y-axis, and then go from there. Okay, so this is all matching. I'll give you a few minutes to try it. Okay, so let's match these up. That first one I got you guys started on, a reflection over the y-axis, is going to make our graph look like exponential decay instead of exponential growth. So this matches graph F. Number two, there's two different things that are happening there. You have shifted the graph right 2 and up 4. If I shift the graph right 2 and up 4, up 4 is probably the biggest one to notice. That means you're going to have an asymptote at 4. That is graph D. You can see that asymptote at 4. We're very close to it there. Okay. Next, y equals negative 4 to the x. That is a reflection over the x-axis. So that's going to flip this graph upside down, and that is graph E has been flipped upside down. Next, number 4, y equals 4 to the x. We've got a plus 3 at the end. So that has moved our graph up 3 units. So the asymptote is something to look at there. We're looking for the graph that has an asymptote at y equals 3, and the one that looks like it's closest to that is graph A. Okay. Next, y equals 2 times 4 to the x. So that 2 is going to be a vertical stretch by 2. This one's a little harder to see, but if you're narrowing it down between C and B are your two options here, you can see that B has been shifted a little bit and C has not. C is still in the same location. C maybe is just a little bit taller. If you imagine some taffy kind of pulling it up a little bit, it's a little bit taller. So that's C. And then you can confirm that if you look at number 6, that plus 3 on the inside shifts the graph left 3 units, and you can see B looks like it's been shifted left 3 units. So our final answers here, number 1 is F, number 2 is D, number 3 is E, 4 is A, 5 is C, and 6 is B. And if any of these you weren't sure about, you've always got that graphing calculator. You can put these equations in y equals, take a look at the graph and match them up that way as well. Okay, so let's talk about the number E. If you've seen the number E before, it's probably been in some sort of scientific formula. E is sometimes called Euler's number. Mr. Euler is the guy that discovered this. It is an irrational number, meaning it goes on forever without repeating or having any sort of pattern to it. It is approximately 2.718. So that's the number that some people use to estimate E, kind of like we say pi is 3.14. E is 2.718 approximately. The biggest reason we see E in exponential functions is because it is called the natural exponential function, and it's used in several types of formulas in finance models. Like I said, scientific formulas like exponential growth and decay of radioactive materials. You may see this written in. So because this number pops up a lot, it gets its own name, and therefore it gets its own exponential function. What's important to remember, though, is that it's a number bigger than 1. So anytime you're talking about the natural exponential function, or e to the x power, it really is just an exponential growth function. And because E is between 2 and 3, you can see that it's going to have a similar shape. It's graphed to the right here between y equals 2 to the x and y equals 3 to the x. It's a little closer to y equals 3 to the x, so that's a good model to look at if you're not sure. So other than it just kind of being a nasty base number, this irrational number, all of the properties for the natural exponential function, or e to the x, are the exact same as all of our exponential growth functions. So don't get too worried if you see that E number there. E in your calculator, if you're looking for it, is located on the TI-84 right above the division key. If you hit second and then your division key, you'll see your E pop up, so you could try that now and hit enter and see this number 2.718 pop up. Another place that it's located in your calculator is right above the LN button, which is to the left of the number 4. If you hit second and then LN, again, is near your number 4 on your calculator, it'll type in E, but it'll also automatically set up an exponent for you. So that's because we often see these written as exponential functions, so it's kind of one less step you have to worry about if you use that button instead. But either one will get you that value of E that you're looking for. Okay. As I mentioned, these pop up in several different kinds of models. One model that we see it used a lot in is compound interest. Compound interest we'll talk about a little bit more later on, but it is where your interest is calculated and then put back into your initial deposit amount. So compound interest is better than simple interest because simple interest, you only earn money on your initial deposit and that's it forever. Compound interest, every time it's compounded, your interest becomes part of your principal, what you start with, and then that money can also earn interest. So you're earning interest on your previously earned interest. And there's lots of different ways that you can compound interest. Annually, 1 time a year it's calculated. Semi-annually, 2 times a year. Monthly, 12 times a year. Daily, 365 times a year. When we're compounding continuously, we're constantly taking the interest and putting it into the bank and being able to earn interest on that. And we use this formula. A stands for your total amount in the bank. P stands for your principal. And principal is just a fancy way of saying your initial deposit, your starting amount. R is your interest rate, and R will be a decimal when we type it in, and you'll see that in a moment. And then T is your time in years. E is just the number E, so you should never be plugging anything in for that. So this formula, sometimes called the PERT formula, you can see why, will calculate the amount in a bank if you are compounding continuously. So let's look at an example of this. Find the amount when a principal, starting amount of $9,000, is invested at a 6% annual interest rate, compounded continuously, that's a key word, for 6 years and 9 months. So we're solving for how much we have in the bank, our A. Our principal, the amount we start with, is 9,000. E is always just E. My interest rate is 6% as a decimal is 0.06. And then my time in years is 6 years and 9 months. So you're going to have to do a little conversion here. 9 months is 9/12 of a year because there's 12 months in a year. So that's 3/4, or the decimal is going to be more helpful here, 0.75. It's 3/4 of a year. So my years are 6 years and 3/4 of a year, 6.75. Now, when I type this in my calculator, I always put that exponent in parentheses, and then you can just type this in exactly as you see it. So in your calculator, this will calculate how much we have in the bank after that 6 years and 9 months, 9,000, and then you're going to hit second and the division key. That'll bring up your E. Then you're going to hit your exponent key, start with the parentheses, and then put everything you see in that parentheses, 0.06 times 6.75. And my calculator tells me that after that amount of time, if I compound continuously, if I get interest on my interest, I get 13,493 point, if I round to 2 decimal places, which we would because it's dollars and cents, 0.72 cents. Okay. Here is another exponential growth or decay model that you're going to see in this lesson. So we've seen y equals a times b to the x, which is just general growth and decay. We also saw the PERT formula a moment ago. Here you have that kind of y equals a times b to the x model, but we've got this extra k filled in, and there's 2 different things that can happen here. The first thing that can happen is if your b value is bigger than 1, so your base is larger than 1, your initial value is a positive value, which it should be. And then if your k value is positive, so if everything's positive and bigger than 1 for our b, this is an exponential growth model. The second thing that can happen is this can represent an exponential decay model. And there's 2 different ways for it to happen. The first way for it to represent an exponential decay model is if the b is a positive base, but your k is a negative number. So if you see that that k or something multiplied by the x is negative, then you have exponential decay. And let me flip back here. We actually saw that happen in a previous example in the notes. In this example here, I had a base that was positive, but I had a negative exponent. And so even though my base was positive, it actually gave us an exponential decay model. So that's why that happened. All right, so that's one way for this to look like exponential decay. The other way for it to look like exponential decay is if your a and your k are positive, but the base is between 0 and 1, which is our traditional model for decay. All right, so here we're just going to name in this problem at the bottom if these are exponential growth or decay functions. So we're going to look at really two things. The a is always going to be positive, so we're going to look at the b and the k value. So starting with this first one, my b value on my base is bigger than 1, and my k value is also positive. That means this is exponential growth. In the next one, I have a base, again, that's bigger than 1, but this time my k value is negative. Because my k value is negative, that makes this an exponential decay function. In C, my base is not the 4, it's the e, but we know that that, again, still is a number larger than 1. And my k value, the number by the x, is negative. So this is a decay model. And then finally, I have a base that is between 0 and 1 and a k value that is positive. That is also an exponential decay model. So if you're not sure with any of these, though, you can always graph it in your calculator. If the graph is increasing from left to right, you know it's going to be growth. If the graph is decreasing from left to right, it's going to be decay. Okay, so here is a problem for you guys to practice. For part A, I actually want you to graph this in your calculator, and there's a window that's written here for you, so that's your x min and your x max. You're going to have to play with that a little bit. Let's just keep our y values between -10 and 10, that standard window. Then I want you to use your calculator to evaluate f of 10 and f of -10. Let's just say 2 decimal places for that is fine. And then finally, I want you to use the graph or your knowledge of exponential growth and decay to determine if this function represents growth or decay. Okay, so let me pull up my graphing calculator here for you guys. Okay, so I'm going to go ahead and type this equation in y equals 12, and then to get my e, remember that's above the division, so we're going to hit second division. That gives me my e, my exponent key, -0.2x. I'm going to change my window a little bit. My x min, I want to be -5, and my x max, 15. X scale, I'm just going to keep the same, and then y min and y max we said we can leave as -10 to 10. So let's hit graph and see what this looks like. There's the picture of my function. At this point, hopefully you can say that this is an exponential decay function. So that's your answer to part C because it's decreasing from left to right. You can also see that here because your base is bigger than 1, but your k value is negative, less than 0. To evaluate these in the calculator, I'm just going to go to my home screen. You can also go to your table of values or calculate a value. There's a lot of different ways to do it. I'm going to hit 12, my e, my exponent key, -0.2 times 10. And then we'll round that in a second. It's going to round to 1.62. Next, I want to type in the same thing, but I want a negative in front of my 10. So I hit second enter there to bring that up again. And you can insert in your calculator. I don't know if we've done this before. If you hit second and then the delete button, it'll allow you to insert something. That's that INS there. Hit enter, and there we go. So now if I'm going to round those to 2 decimal places, my answer for f of 10 evaluates to 1.62, and F of negative 10 evaluates to 88 point, I would round that to 67. And again, this is an exponential decay function. That's our answer to part C. Okay, let's look at an application problem. This is an application about purchasing power. It says a retired couple has a fixed income of $60,000 per year. The purchasing power, which is the real value of their money after T years of 5% inflation, is given by the following model. So they've already written the equation for you, and we're going to use this to answer some questions. Real value of money means what it's actually worth. So for example, if I had, I don't know, I'm just going to make up some numbers here, $5 back in 1940, today that wouldn't be worth $5 worth of merchandise. It might be worth a lot more than that or a lot less than that. So that's what they're talking about here, the real value of the money. If they have $60,000 now, what's that actually going to buy them later on worth of merchandise, okay? Or a value of something if they invest. So my model is an exponential function. This is the model y equals a times b to the x that we're seeing here. A is my initial value, $60,000 is what they start with. B is the growth rate, 0.95 is what we're multiplying by from one term to the next, and T is our time in years. Part A says, what is the purchasing power after 4 years? And again, years is our T. So all we're going to do is plug 4 into our equation, 60,000, 0.95 to the 4th power. And I always put it outside the parentheses, but you'll notice this book and my math lab sometimes likes to put it inside the parentheses there. And you're just going to type this in your calculator, 60,000 times 0.95 to the 4th power. I get, and again, I'm going to round to 2 decimal places here, $48,870, and it's 0.375, so I'm going to say 0.38. So $60,000 today will buy us 48,000 and change, maybe $49,000 worth of merchandise based on inflation in 4 years from now. Okay. Then let's test values in this function, determine when the purchasing power will be less than 30,000. So when it says test values, probably your calculator is going to be the best thing to use here. Okay. And we're just going to type our equation in. Actually, I'm going to show you a little shortcut here. Let's put our equation in y equals, because you can do this in your standard window and just keep typing numbers in, but the calculator evaluates things so quickly for us. So, that's an exponent there. There we go. So notice I put this in y equals, and instead of a t, I just used an x. If you go to table, it'll evaluate very quickly for you. And actually, let me reset one thing on my table so mine looks like yours. If your table's ever weird, you hit second window, and it brings you to the screen. Table start 0, triangle, TBL, that means change in the table 1. These are your default settings. So now if you go to your table, you'll see some values that we're looking for. So again, after 0 years with starting amount, that was 60,000. That's no surprise. We also found 4 a couple minutes ago, about 49,000. We're trying to figure out when is the purchasing power going to be less than 30,000. So one thing I could do by hand is I could plug in 5, plug in 6, plug in 7, and figure out the first year that we're below 30,000. But this table of values gives me a really quick way to figure that out. Now you'll notice the first time I get below 30,000 is year number 14. So in how many years will it be less than 30,000? My answer is in 14 years. And you could always test 14 by plugging in the equation, and you're going to see you get that value of 29,260. Okay, let's look at another one. This is a radioactive decay problem. I mentioned that as an example where you see a lot of E's used. So that's why we see an E in this problem. It says a breeder reactor converts a stable uranium-238 into an isotope plutonium-239. The decay of this isotope is A of T equals 100 times E to the giant decimal there times T, where A of T, I'm going to underline what my variables stand for, is the amount of the isotope, at time t in years. 100 grams is the original amount, and they didn't have to tell us that because that's the initial value that we see in this equation. We can also at this point say that this is going to be a decay function, and anytime you're talking about radioactive material, it's going to be a decay function. But we know that because my base, my B, is E here, it's bigger than 1, and because my K value is negative, that's what's making this decay. Okay, so the first thing we're going to do, and we're just going to use the calculator for these, is we want to know how many grams remain after 100 years. So I'm just going to go to my standard window here, and I just hit second quit to go back to that standard window. I'm going to clear out what I have. I'm going to type this equation in, 100, get my E, second, and the division key, my exponent, negative, make sure I get all my zeros here, 0. Looks like there's 4 zeros there, 2876, and then 100 years, that's my T, so I'm going to put a, parentheses 100. Okay, so the question is how many remain? 99.7 remain. Just drag that over for right now. We'll come back to it. Okay, then we want to graph this function. Okay, so let's put this in y equals, here we go. Okay, so then we want to graph this function. We're going to put this in y equals, and I clear out what we had in there. Again, my equation was 100 E, get my exponent, negative 0.402876, and instead of a T, we're just going to put an X there. Okay, and we were told a certain window to use, so the next thing I'm going to do is hit window, and T is my X's here. We need to use values from 0 to 50,000. Okay, and my Y values, I'm going to change these a little bit. So my maximum Y value, I'm going to make 100 because that's the starting amount, and we know it's decaying. Now I can't have a negative amount of something, so I'm going to say everything from 0 to 100 would be a nice picture here. If I hit graph, you can see there's our model, and this is what I was talking about in the calculator, where sometimes it looks like you're going to touch the axes. You really don't there. It's getting infinitely close, but our calculator only has so many pixels, so that's why we're seeing that. So you got to make sure you know better when you look at those pictures. You're not actually touching that. Okay, so answering the first couple questions with what I've found so far, 99.7 is the amount of grams after 100 years. Graphing the function, and this was from 0 to 50,000, and then from 0 to 100 is where the graph started at. You can again see 100, the starting amount is that y-intercept, that a value. Okay, finally, let's look at part C. Often when we talk about radioactive decay, we talk about a half-life. A half-life is how long it takes for half of the material to remain. So here I started out with 100 grams of the element, okay? If I'm talking about a half-life, we're trying to really figure out when do we have half of it left. So in this case, when do we have 50 grams left? How long does it take for 100 grams to be halved, turned into 50 grams? So we can again use our table of values to help us here. We just have to know what we're looking for, and we're looking for half of the original amount, 50. So let's scroll down here. And this may take a while. So let's kind of jump ship here a little bit. I'm going to go to table set, and let's scroll to, like, instead of 67, let's scroll to 200. And let's see where we are. Okay, we're still in the 99s. This is going to take forever. All right, so I don't want to play with that. Let me show you another way you could do this. Go into y equals, and we're going to find an intersection. This is the intersect method that we used before. I want to know, when does this graph reach 50? So let's hit 50 and graph it. There we go. The point where my exponential function crosses that line, y equals 50 is what we're looking for. So we're going to calculate the intersection. Second, trace. Hopefully you remember doing this. Number 5 is intersect. And there's one intersection here, so we just need to hit enter 3 times. Enter, enter, enter. And you can see our intersection between my original function and when y equals 50 is about 24,101. So part C, how long is this going to take? It's going to take approximately 24,101 years to be half of the original amount. So you can imagine if I kept scrolling there, how long that would have taken. So good thing we didn't do that. So if you do feel like you've got a pretty large or a pretty small number that you're looking for, that's a great way to do that. So let me just review that one more time for you. If there's a specific value that you're looking to estimate, graph your original function and the value that you're trying to find when it's equal to that or below that or above that potentially. So in this case, it was 50. And then we hit second trace, intersect number 5, and then you just hit enter 3 times. Enter, 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 and it'll give you that intersection and that approximate value. When we do exponential equations in a couple sections, we'll actually be able to solve for that algebraically without having to do all this estimation stuff in the calculator, which can be a little tedious. But for right now, the calculator is a good way to get that, and it's going to be nice to be able to check our answers later on. Okay, here is the last problem for you guys to try. This is a population problem. It says the population in a certain city was 53,000 in the year 2000, and the future size is predicted to be 53,000 times e to the 0.015 t people, where t is the number of years after 2000. Is it increasing or decreasing? So you want to think about, is that growth or decay? You want to estimate the population in 2005 and 2010, and just remember there that t is the number of years after 2000. And then part D, you want to find the average rate of growth. Okay. So actually, let's do part D together. I want you guys to do A, B, and C, and then we'll do that last piece. All right, so go ahead and try those first 3. Okay, so is it increasing or decreasing? Again, we just want to know, is it growth or decay? So we're going to look at the model here, or you can look at the graph. If you looked at the graph, that would give you a clue as well. My base, E, is a number bigger than 1. My K value here is also positive. So this is an exponential growth model, and it is increasing. Okay, next in your calculator, we're going to use T equals 5 for 2005 and T equals 10 for 2010. You can type that in the home screen in your calculator, or you can use the table of values. So I'm going to go to y equals. I'm going to use my table again here. Type in my equation, 53,000. E, bring up my exponent, 0.015, and then an x instead of a t. And then my table was a little messed up from before, so I'm going to hit second window and just start my table over. And I'm going to start my table at 0, change in the table at 1. So now if I go to table, I can find the year 5 and the year 10. Let's just drag those over. My populations will be in 2005, which is number 5 on my chart here, 57,128 people. In 2010, or if I plugged 10 into this equation, and you could do that always by hand if you want to as well, you get approximately 61,577 people. Okay, part D, I said we were going to do that together. What is the average rate of growth between 2000 and 2010? Oop, wrong thing. Hold on one second. Let me hit the right button here. Okay, so to do this, we're just going to use our average rate of change formula from a previous lesson. So average rate of change, remember, was like our slope formula, y2 minus y1 over x2 minus x1. And here we're trying to find the average change between 2000 and 2010. So we need to know, first of all, what the year is. So the year is either year 0 in this function for 2000 or 10 for 2010. And then the y's that go with those are the populations for each. Well, in 2000, we knew the population we were given was 53,000. And in year 10, or 2010, my population was 61,577. So setting up this formula now, y minus y would be 61,577. Sorry about all the commas there. I'm comma happy, I guess. Minus 53,000, y minus y, over x minus x, 10 minus 0. And then we can simplify that. If I simplify the numerator, 61,577 minus 53,000, I get in my numerator 8,577. Divide that by 10 minus 0 is 10. I get approximately, if I round to the nearest person here, 858 is the average rate of growth. So approximately the population of this certain city is growing by 858 people a year is what this model tells us.